Hi, I'm Dr. Hay. I'm going to show you how to solve a classic physics problem called the ballistic pendulum. So what the ballistic pendulum is, it means that a bullet is being fired at a pendulum. The bullet is going to completely embed in the mass hanging at the pendulum. It's like a wooden block. And it's going to have an inelastic collision, which means it's going to completely stick. All right, the bullet's going to go into the mass. The mass is going to swing sharply up this way. And the question in the ballistic pendulum is, how high does the mass go? All right, so you can see that once the mass embeds inside the pendulum, that pendulum is going to swing up to a certain height, and our job is to find this height. This is the mass of the bullet plus the mass of the block. Okay, so we have basically two distinct kinds of concepts happening here that we can use to solve this problem. We have two kinds of conservation laws happening here that we can take advantage of. First, we have a momentum problem. This is an inelastic collision. The next kind of problem we have is an energy conservation problem, because now we have something moving and it's going to go up high. In other words, it's going against gravity. And now this is an energy problem. So we're going to use momentum conservation in the first part and energy conservation in the second part to solve this problem. Let's start with momentum conservation. At first, the second block is not moving, so it has no momentum. What we're going to do is set the initial momentum, which happens to be the momentum completely from the bullet, equal to the final momentum, and the final momentum is what happens right as soon as this block starts moving. So let's give this a final velocity before it starts swinging upwards. So we're just interested in what happens right before the bullet hits and right after it hits. The initial momentum is the momentum completely from the bullet. M1 V, let's call it V1I. It's the initial velocity for mass 1, which we're going to call the bullet. Now that is equal to the final momentum, equals the final momentum, and the final momentum is equal to the mass of the two objects together times their velocity. Let's call that V2. Okay, so we can use this equation to solve for V2, because we have, it's actually this equation, M1 V1I equals this portion over here. So we know everything here, we know the two masses, and this is our only unknown. So let's solve this equation for V2. Okay, I've used momentum conservation to solve for the velocity of the two objects together as they begin going upwards. So I've just erased the momentum pieces here so that you could see this is one single equation. The next part of our problem is now kinetic energy is converted completely into potential energy, because for a moment it stops at the top before it comes back down. So our initial energy is the two masses with this velocity, that's a kinetic energy, and it goes up mgh, and the m is the combined two masses. How far up do they go? So let's solve the energy problem. So now I've written that the kinetic energy that it starts with at the very bottom here is equal to the potential energy, the complete energy that it's got here. I'm sorry, that's a V2 because that's what I called it down there. Now I can find H using this equation. It had no potential here, and it has all potential here and no kinetic. I have solved this equation for h, and I have also put in v2, which I solved for down here with my momentum conservation problem. So now I've got the height is equal to all of this stuff. Now I can cancel things out. So now I've rewritten this problem without the things that I canceled out here. So now h is equal to this function here. And if I had the mass of the bullet and the mass of the wooden block and the initial velocity, then I could plug in numbers for this and get an actual height for my pendulum. And now you've seen how we can solve the ballistic pendulum problem using momentum conservation and energy conservation.